So we're going to start with number 8 here. Send pilot in the air show. Loop to loop. Divert circle rate assist. And this performance pilot whose weight is this contains a constant speed. So, are there forces mentioned? Yes. So we know we're going to need a force diagram. I think I'll start off by stealing that image so I don't have to redraw it. Speed of this, times half point, determine apparent weight. Now, what do they mean by apparent weight? What do we perceive as feeling our weight? Well, yeah, our weight would be the normal, would be the force of gravity, but we experience that by feeling the normal force. Remember, that's what a scale measures, is actually how much it's pushing up on you, not how much you're pushing down on it. So I would start off by starting to understand that, saying something like apparent weight is normal force. And that there must be a force towards the center of the circle so that he can move in a circle. Since he needs to accelerate. Towards the center. I mean, that's kind of the big idea here. To move in a circle, you must accelerate towards the center. So, that means that you have to cause that acceleration. You need to have a net force towards the center. At least part of it. We didn't really, because we're going through this so fast, we're not going to really deal with, hey, what if the plane was speeding up while it went in this circle? But that would provide another level of complexity and reality to it, because you're not going at the same speed. You are speeding up or slowing down. And, but just for simplicity, we're going to keep it a little at the simpler case. So, the force diagram here, one thing to make sure that you have on it, are we only doing the top and bottom? That's it. At what speed will the pilot experience weightlessness, and lowest point and highest point? Okay. So I think we'll do A and C and then come back to B. So, let's see, let's draw some forces here. The plane would have weight down, or the person. Are we dealing with the person? Yeah. So, the weight of the person is always going to be down, right? No matter what. But they also are going to have here a normal force upwards, and this one may have a normal force pointing in this direction. Yes, with the surface. Like right now, there's a normal force on your elbow because it's on a flat surface, on your backside, on the bottom of your feet. Anywhere there's a surface, it's the surface's reaction to that applied force. So, And let's see. And the if he goes too slow, the one I'm looking at is the normal force up top. It's going to be downwards. And then don't forget that in every force diagram you have to have an acceleration if there is one. And in this case, that's the centripetal acceleration. Remember that those are C's. I was trying to write small. Remember, centripetal just means pointing towards the center. But we're going to need that centripetal acceleration to be able to turn the corner. So, this is number what, 7? Good. Number 7. This is 8. There we go. And let's see, the pilot, what do they tell us? They tell us the radius of the circle, his weight, and the constant speed. And they want to know the apparent weights up top, so let's do A first. And we start with Newton's second law. And we have, which way do you, for the top position, which way do you want to call positive? I'd call downwards or towards the center of the circle positive, because all three things are pointing that way. So in this case, I have force normal plus his weight, which we can label as F sub G. That's what I don't know why I put mg this morning in here. It should be F sub G. Sorry. Definitely Friday morning. Equals his inertia times the acceleration, which is centripetal. And we're looking for the normal force. And in this case, the normal force equals the minus F sub G. Yes. Okay. And then the things for remember we have a couple different equations we can pick for the centripetal acceleration, either relating the speed to the radius, or the radius to the period. They tell us the speed, so I'm going to pick the AC equals V squared over R. So I'm going to have force normal equals the inertia times V squared over R minus his weight. They tell me his weight, right? The problem, mine is 696 newtons. So this is 696 newtons. They don't tell me his inertia, right? But I know that, here as a side note, I know that his weight is his mass times gravity. So if I want his inertia, I can do F sub G divided by G equals his inertia, right? So for his mass, I'm going to do 696 newtons over 9.80 newtons per kilogram. B, they tell me, right, 2.05 times 10 to the second, so 205 meters per second for mine. Don't forget to square that. And then my radius, they tell me also, is 3,350 meters. 3,350 meters. That's all kind of jammed up in there. Sorry about that. So let me double check that I get the right answer on that part. All right, so that mine worked. My solution there. I'm gonna flip to doing part C now. The lowest point, determine his weight, and then come back to part B. So this will be part C here, and I'm going to start off the same way, except this time I'm still going to take towards the center as positive, so I have force normal minus F sub G equals MAC, and therefore when I rearrange this for force normal, I get MAC plus his weight. And that's why I flip to this part next. It's because you can see that the only difference here in our two equations is that our gravity is pointing away from the center now rather than towards the center. So it's the only force providing this centripetal force is part of the normal force. So mathematically, it's just the same relationship, except the gravity is pointing in a different direction now. So, and then for part B, going back to B, you have they're asking now, at what point would he feel weightless? What speed? And that would be, remember, our perception of weight is the normal force. So that would be when the normal force in part B is 0. So kind of skipping, part A is 0, so kind of skipping all of the preliminaries. We can go directly to our relationship for force normal. We can't use the relationship in point C, part C, because we never get 0 for the normal force at the bottom. Because even if I stopped moving, or I wasn't moving in a circle, I'd still have the gravitational part of the equation in there. So really what I'm looking at is I'm looking at force normal equals mv squared over r minus f sub g, and this force normal is going to be 0, so I'm looking at when mv squared over r equals the weight, and I can rearrange that and do it that mv squared over r equals mg. Get rid of my m's, and that's why whether whoever's in the plane is going to feel that same weightless. And so then you have v squared over r equals the acceleration due to gravity, little g, and you can plug in your numbers and solve. If you need help on the individual math, let me know. I'll be glad to come around and help. Alright, so number 4. Remember, a jet fighter at this, just below the speed of sound, makes this turn at this. Oops, kilometers. What should I make sure I put that in? Meters. What's centripetal acceleration in G's? So they say, and a lot of times they'll ask for you to do it in G's just to make it more understandable, or more relatable, I guess is a better word. But the why for this one, well, first off, do we need a force diagram? No force is mentioned, so we fall under the original rubric. So here, let's see, the jet is moving in a circle, so must accelerate towards the center. And that's called centripetal. I'd also probably put in there, show I understand that the faster or the smaller, you guys okay back there? The radius, the higher the acceleration. So showing that I realized that not only does the speed that the jet is moving, but also how big of a circle affects the acceleration, the rate that that velocity has to change. So starting with part A, 300 meters a second, for me, 1.95 kilometers an hour. So they tell me the speed and the radius, so I'm going to use that AC, part A, is V squared over R. And AC, I'm going to use, my V is going to be 300 meters per second. Don't forget to square it. My R is 1,950 meters. This is 1.95 kilometers. And I'm going to find out a value for AC, and that will be in meters per second squared. Once I do the math there, and then take my value for AC, and I want to put it in bundles of G. So I'm going to divide it by the value of G, 9.80 meters per second squared, and I'll get my answer in how many G's that is. Then, moving on to part B, most pilot makes so now he's got 10 G's while flying at this. Was the radius of his turn. So, same approach, just no different parts of it now. V squared over R. I would rearrange for R and get R is V squared over AC. And know that my V is given to me, whatever it is. My AC is told to be 10 G, so it's 10 times 9.80 meters per second squared. And solve for R. And then I'll do it for number 4. Let me know if you need help with the individual mathematics involved. Alright, so now on to number 5 here. This unbanked plank flat curve. And it's rated at this maximum speed. To the flat curve rated speed. Now, if you think back to the first day on circular motion, we watched a little video that showed that was an illustration of going around a flat curve, which showed that the frictional force was pointing towards the center of the curve, and that was what was providing the force needed to have an acceleration towards the center. So this is one of those that you could do a force diagram for, probably would be best to, but you don't necessarily need it in your Y. I'm going to put one in my Y just because my brain works that way. But if you didn't have one in your Y, you wouldn't be graded down for it. So this is number 5. And I'd first start off showing that you understood that to go in a circle, you must accelerate towards the center. On this flat corner, friction provides the force that creates the acceleration. going to put that the surface is the same in both cases. And that's because the one thing that they need to share in common is the what's creating the frictional force. So, my diagram, I'm going to do kind of a side view where the car is coming at me. So there's my car, and it's coming at me, so we'll draw the grading of the front here, the windshield wipers, and it's moving towards me, so we'll give it a velocity towards me. And in this case, with this velocity, the center of the circle we'll put over here to the left. So the acceleration needs to be in that direction. It's going to have weight down and the normal force up. And it will have a frictional force in that direction. And that's the force that's going to provide the centripetal force. So the force towards the center that's needed to create that acceleration. I'm going to use that centripetal acceleration is v squared over r. And the fact that, well, yeah, I'm going to use forces to solve it. So forces equals ma. This is part A, by the way. And I have my frictional force equals my inertia times my acceleration centripetal. Both those are in the same direction. My frictional force would be mu force normal, MAC, which would be v squared over r. Mathematically, one more substitution. The normal force is up. It's going to be equal to the weight, which would be mg, mv squared over r. The m's cancel out. That's why the size of the car doesn't matter. And you're left with that mu times g is going to equal v squared over r. And in both cases, this is going to be true. That's why it's important that the surface is the same in both cases. So they're asking for 150 meters. The rated at this was maximum speed to the radius of the curve B rated. So this is true in both cases. So what I'm going to do is simultaneously do those. So in case 1, we have that mu times g equals 150 and 33 for me. 33 meters per second squared over 150 meters. In the second case, we have that mu g equals v squared over 62 meters. Mu and g are constant, so your next step would be to set those two equal to each other and solve for your v squared. All right, let me know if you need help individually on that one.